Disclaimer.
There's a dangerous assumption baked into almost every conversation about artificial intelligence. The assumption is that AI is infinite scale, infinite growth, infinite efficiency. That assumption is wrong, because AI is not just software. It is one of the most material-intensive systems humanity has ever built. And right now, AI has run headfirst into something it cannot code its way around, a physical limit. This is the moment where the narrative breaks. For years, the AI story was clean and comfortable. Smaller chips, faster processors, cheaper compute, limitless expansion. But underneath that digital story sits a brutal physical reality. Every AI model runs on massive data centers, dense electrical systems, ultra-efficient power distribution, heat management infrastructure operating at extreme loads. None of that runs on ideas. It runs on metal. And one metal sits quietly at the center of all of it: silver. This is not a theory. It is not a metaphor. It is not a future risk. It is happening now. Because AI demand is scaling exponentially, not gradually, while the materials required to support it are not. That mismatch is not something markets solve politely. They don't smooth it out. They don't average it away. They don't negotiate with it. They collide with it. And when exponential demand collides with linear or declining supply, the result is not equilibrium, it's constraint. This is why something feels off in the AI narrative right now. Data centers are expanding faster than grids can support. Power demand projections are being revised upward every quarter. Infrastructure costs are exploding. And procurement teams are quietly scrambling for inputs that were once taken for granted. Silver is one of those inputs. Not because it's fashionable, not because it's speculative, but because it performs functions inside AI infrastructure that cannot be easily replaced without degrading performance. This is the first time AI has encountered a limit it cannot solve with software optimization or capital alone. Money can build data centers, money can design chips, money can hire engineers, but money cannot instantly create physical silver. And when the most capital-intensive industry on Earth runs into a material it cannot scale, the rules change, not tomorrow, not in headlines, but in procurement decisions happening quietly right now. This is not about price, this is about feasibility. AI growth is no longer constrained by imagination. It is constrained by physics. And once a system hits a physical ceiling, the next phase is not debate, it's triage. One of the most persistent myths about artificial intelligence is that it scales the way software does. That belief is comforting and completely wrong. Software feels weightless. You copy it, you deploy it, you update it. But AI is not software in isolation. AI is a physical system disguised as a digital one. Every breakthrough model, every leap in capability, every increase in performance rests on an expanding base of hardware and energy infrastructure. That infrastructure is not optional, and it is not abstract. AI runs on servers stacked into warehouses the size of small cities. It runs on power systems that consume electricity at the scale of industrial plants. It runs on cooling systems designed to move heat continuously without failure. This is why the idea of infinite AI scaling was always an illusion. It worked when growth was small enough to hide behind efficiency gains. It worked when demand was niche. It worked when infrastructure growth could be absorbed quietly. That phase is over. Today's AI models do not scale linearly. They scale exponentially. Each generation requires more compute, more energy, denser circuitry, tighter tolerances, which means more physical inputs at every layer. And this is where the myth collapses, because physical systems do not scale like code. They are bound by materials, manufacturing timelines, energy constraints, supply chains. You can't spin up a data center the way you spin up a server instance. You can't double power density without doubling stress on every component that carries current or dissipates heat. This is where silver enters the story. Silver is deeply embedded in the physical reality of AI, in places where performance margins are thin and failure is unacceptable. It appears in high-efficiency electrical contacts, advanced circuitry, thermal management systems, power distribution components. These are not decorative uses. They are chosen because silver's properties allow systems to operate under extreme load without degradation. When AI demand was small, silver use was manageable. When AI demand explodes, silver becomes a bottleneck. This is why AI is encountering resistance for the first time. Not from regulators, not from ethics boards, not from public opinion, from physics. And physics does not negotiate. The belief that AI is just software allowed everyone to ignore the material foundation underneath it. But once that foundation starts to strain, the illusion disappears. What remains is a simple, uncomfortable truth. You cannot scale intelligence faster than the materials required to support it. And silver is one of those materials. That is why AI's next challenge is not innovation. It is resource constraint. To understand why silver matters to artificial intelligence, you have to stop thinking about AI as an app and start thinking about it as an electrical system under extreme stress. AI does not fail because of bad code. It fails because of heat, resistance, and power loss. Every large AI model runs inside data centers designed to push physical limits. Maximum power density, minimal latency, continuous uptime. Zero tolerance for electrical instability. In that environment, small inefficiencies become catastrophic at scale. This is where silver becomes irreplaceable. Silver is used where electricity must move fast, clean, and reliably. Inside AI infrastructure, silver appears in high-performance electrical contacts and connectors, advanced printed circuit boards, power distribution units, switches and relays handling extreme current loads. In these components, resistance is not an academic concept. Resistance means heat. Heat means failure. Failure means downtime measured in millions of dollars per minute. Copper is cheaper, but copper carries higher resistance. Aluminum is lighter, but aluminum introduces losses and durability issues. Other substitutes degrade performance under sustained load. Silver is chosen not because it is precious, but because it works. As AI data centers push toward higher compute density, electrical tolerances tighten. A fraction of efficiency gained in each connection compounds across tens of thousands of servers, millions of connections, continuous 24/7 operation. The compounding effect is invisible to casual observers, but it is everything to engineers. Cooling systems add another layer. AI servers generate enormous heat. That heat must be moved away instantly, continuously, and safely. Silver's thermal conductivity makes it valuable in heat dissipation interfaces, specialized cooling components, high-performance thermal pathways. Again, substitutes exist, but they carry trade-offs. Trade-offs that reduce reliability, trade-offs that increase maintenance, trade-offs that shorten component lifespan. At small scale, those trade-offs might be acceptable. At AI scale, they are not. Now layer on redundancy. AI infrastructure is built with redundancy everywhere. Backup power, duplicate pathways, failover systems. Redundancy multiplies material use. Every backup doubles demand. Every safety margin increases metal intensity. This is how silver demand grows quietly, not through headlines, through engineering requirements. And unlike software optimizations, these requirements do not disappear with better algorithms. They intensify. More compute means more power. More power means tighter electrical tolerances. Tighter tolerances mean higher quality conductive materials. This is why silver demand inside AI is not linear. It accelerates as systems scale. And this is the key insight most discussions miss. AI does not just consume silver. AI concentrates silver demand into the most stressed parts of the system. The concentration creates pressure long before the total numbers look dramatic. By the time silver shortages become visible in aggregate statistics, the constraint has already become operational. This is why AI demand for silver is not a future problem. It is a present one. Now we need to put two curves on the same page, because this story only becomes obvious when you compare how fast AI demand is growing with how slowly silver supply can move. AI demand is not incremental. It doesn't grow by a few percentage points a year. It grows in step functions. A new model launches, compute requirements jump. A new deployment phase begins, data center capacity multiplies, a new national strategy forms, infrastructure spending accelerates. Each step compounds the previous one. This is why power demand forecasts for AI keep getting revised upward, not because analysts were careless, but because exponential systems are almost always underestimated. Silver demand inside AI follows the same pattern, not because each server uses dramatically more silver than before, but because there are vastly more servers. Power density is increasing, redundancy requirements are expanding, so even small increases per unit become massive increases at scale. Now compare that to supply. Global silver supply is flat to slowly declining. It does not surge when demand surges. It does not respond to headlines. It does not scale with enthusiasm. Mining output changes slowly, constrained by geology, permitting timelines, capital cycles, environmental limits. Even optimistic scenarios show supply growth measured in single digits, over years. This is the collision. On one side, AI demand growing in leaps, infrastructure scaling aggressively, governments and corporations racing for advantage. On the other, silver supply that can barely maintain current levels. Markets can absorb imbalances for a while. They cannot absorb structural divergence. At first, the gap is invisible. Demand is met by inventories, by recycling, by delayed delivery, by substitution where possible. But those buffers are finite. Once they thin out, the system stops behaving smoothly. Not all buyers feel it at once. The largest, most strategic buyers adapt first. They secure supply. They lock contracts. They remove material from circulation. Smaller buyers feel the pressure later, through delays, higher premiums, and reduced access. This creates a false sense of stability because the system doesn't run out of silver overnight. It fragments. Some get supply, some don't. And that fragmentation is the clearest sign that a market is under strain. AI accelerates this process because it does not tolerate uncertainty. A data center expansion cannot wait for the market to rebalance. A national AI initiative cannot pause because materials are scarce. So the response is not to slow demand. It is to preempt supply risk. This is why the silver market feels calm on the surface while pressure builds underneath. The demand curve has already bent upward. The supply curve has not moved. And when two curves diverge long enough, the resolution is never gradual. It is abrupt. At this point, most people reach for the same reassurance. If demand rises, miners will just produce more. That belief is comforting and dangerously inaccurate. Silver supply does not scale the way demand does because silver is not mined on its own terms. The majority of the world's silver does not come from silver mines. It comes as a secondary byproduct of mining for other metals. That means silver production is controlled by markets that have nothing to do with AI, technology, or energy transition. If copper prices fall, copper mines slow down. If lead or zinc demand weakens, those operations pause. And when they do, silver supply drops with them, regardless of silver demand. This creates a fundamental mismatch. Even if AI demand for silver doubles, miners cannot simply double silver output. There is no dial to turn. There is no switch to flip. Primary silver mines exist, but they are limited, capital intensive, and increasingly constrained by declining ore grades. Over the last several decades, the easiest silver deposits were mined first. What remains requires deeper excavation, more energy, more water, more processing per ounce. This means each new ounce is more expensive and slower to produce than the last. Time is the real constraint. From discovery to production, a new mine can take 10 to 15 years. That timeline does not care about AI adoption curves. It does not care about quarterly earnings. It does not care about geopolitical urgency. Supply responds on geological time. Demand moves on technological time. Those two clocks are incompatible. There is another layer to this constraint that rarely gets discussed. Environmental and regulatory pressure has intensified across the mining industry. Permitting is slower. Community opposition is stronger. Capital requirements are higher. Even when deposits exist, bringing them online is no longer guaranteed. This further reduces the system's ability to respond quickly to demand shocks. Now add one more complication: recycling. Silver recycling helps, but it is not a silver bullet. Much of the silver used in AI infrastructure ends up embedded in complex systems, circuit boards, solder, microcomponents. Recovering it is difficult, expensive, and slow. Recycling increases supply at the margin. It does not solve exponential demand. This is why silver supply is fundamentally inelastic. It can bend slightly over long periods. It cannot surge. And when a system with inelastic supply meets a system with accelerating demand, the outcome is not balance. It is pressure. Pressure that builds invisibly. Pressure that expresses itself first in access, not price. Pressure that eventually forces repricing or rationing. This is not speculation. It is how constrained physical systems behave every time. Up to now, we've talked about silver inside servers, chips, and data centers. But this is where the story gets much larger and much more dangerous. Because AI does not just consume electricity, it reshapes the entire power system around it. Every new AI data center is not a passive load. It is a stress test for the grid. AI facilities demand continuous power, extremely high reliability, minimal voltage fluctuation, instant failover capability. To support that, utilities are forced to upgrade infrastructure far beyond normal requirements, and those upgrades are silver intensive. High-capacity transformers, switchgear, and grid control components all rely on high conductivity materials to handle increased load without failure. As power density rises, tolerances shrink. Small inefficiencies that were once acceptable become unacceptable. That's when silver use increases, not because it's cheaper, but because it's safer. Now add redundancy. AI data centers are designed to never go dark. That means multiple power feeds, backup substations, redundant transmission paths, on-site energy storage. Every layer of redundancy multiplies material demand. One grid connection becomes 2. One pathway becomes 3. Every just-in-case design choice compounds metal usage. And this doesn't stop at the data center fence. Grids feeding AI infrastructure must be hardened upstream. That means upgraded transmission lines, reinforced substations, advanced monitoring systems, improved fault isolation. All of these systems rely on high-performance conductive materials. And silver plays a role where reliability matters most. Energy storage adds another multiplier. AI growth is pushing demand for battery systems, power smoothing, load balancing. Silver is used in battery technologies and power electronics that manage rapid charge and discharge cycles. As grids become more dynamic to support AI, material intensity increases again. This is the hidden compounding effect. AI doesn't just increase silver demand directly. It forces the entire electrical ecosystem to upgrade, and those upgrades are silver-heavy in critical points. This is why AI demand for silver is underestimated in most projections. Analysts often count servers, chips, direct electronics. They miss grid reinforcement, redundancy layers, energy storage systems, power management infrastructure. But these indirect demands often exceed the direct ones. This is how physical constraints sneak up on systems, not through one dramatic shortage, but through thousands of small, rational engineering decisions that all point in the same direction. And once those decisions are made, demand doesn't reverse, it locks in. This is where the consequences become unavoidable. When a sector as capital-rich and strategically important as AI encounters a material constraint, it does not compete politely. It outbids, not recklessly, not publicly, but systematically. AI developers do not operate on commodity market logic. They operate on mission logic. If access to silver determines whether a data center can come online, the question is no longer, is this metal expensive? It becomes, what is the cost of delay? And the cost of delay in AI is enormous. A single postponed deployment can mean lost market share, lost national advantage, lost technological leadership. Those costs dwarf material prices. So AI-linked buyers behave differently. They sign longer contracts. They pay premiums for priority access. They accept higher upfront costs to eliminate uncertainty. This behavior does not show up as a bidding war on a public exchange. It shows up as allocation pressure. Some buyers get supply without issue. Others face delays, minimum order requirements, or outright refusal. The market doesn't run out of silver evenly. It stratifies. Large strategic buyers secure what they need. Smaller users are pushed to the margins. This is the most misunderstood phase of a constrained market. Because on the surface, silver still exists. You can still find it. You can still trade it. But the rules are no longer equal. Priority replaces price. And once priority enters the system, the market is no longer free in the classical sense. This has cascading effects. Manufacturers downstream face rising input uncertainty. Costs become unpredictable. Production schedules become fragile. Some firms adapt by reducing silver usage where possible, accepting lower performance. Others exit entirely, unable to compete for supply. Over time, this reshapes entire industries. Not because of innovation, but because of access. AI accelerates this process because it absorbs silver quietly and continuously. Unlike speculative demand, it does not release metal back into the market. Once silver enters AI infrastructure, it stays locked in for years. This creates a one-way flow, from circulation into permanent deployment. And one-way flows are dangerous for markets built on turnover. Eventually, even the largest buyers feel the strain, because as allocation tightens, the system must choose who gets supply, who waits, who goes without. That is not a pricing decision, it is a power decision. And when markets reach that point, they rarely return to equilibrium on their own. Every economic era eventually runs into a wall it cannot negotiate with. Not a political wall, not a financial wall, a physical one. Artificial intelligence has now reached that point. For years, the story was that AI would be limited by regulation, ethics, talent, capital. Those limits turned out to be soft. What AI is facing now is not soft. It is a hard constraint, the kind history does not forgive optimism about. Because no amount of capital can instantly create physical silver. No policy can accelerate geology. No software breakthrough can substitute fundamental material properties at scale. This is why this moment matters. When a system built on exponential growth collides with inelastic supply, something must give. Historically, there are only three outcomes. Demand is rationed. Price is violently revalued. Control replaces markets. Usually it's a combination of all three. Now, we've seen this before. Oil in the 1970s did not simply get more expensive. It reshaped geopolitics, currencies, and industrial planning. Rare earth elements did not just spike in price. They redefined trade relationships and exposed dependence. Semiconductors did not merely become scarce. They triggered national security strategies and state intervention. In each case, the mistake was the same. People assumed the future would look like the recent past. They assumed markets would adjust smoothly. They assumed supply would respond. They assumed innovation would bypass constraints. It never did. Silver is now entering that same historical channel, not as a headline, not as a crisis, but as a constraint embedded deep inside the most powerful growth engine of the modern world. AI cannot slow down voluntarily. Competition does not allow it. National strategy does not allow it. And when demand cannot slow and supply cannot accelerate, the system must restructure. Quietly at first, procurement contracts lengthen, inventories disappear from circulation, priority access replaces open availability. Then, suddenly, markets fracture, prices gap, access becomes political. This is why focusing only on today's price misses the point entirely. The real story is not what silver costs. It is who can get it, who can't, and for what purpose. Because once a material becomes essential to technological dominance, it stops being just another input. It becomes leverage, and leverage changes behavior long before it changes headlines. The warning here is not dramatic, it is structural. AI has grown faster than the physical systems designed to support it. Silver is one of the first places that mismatch is becoming visible, not because of speculation, because of necessity. History shows us how this ends, not smoothly, not gradually, not comfortably, but decisively. And by the time the world agrees on what happened, the decisions that mattered will already be locked in. That is the nature of hard constraints. They do not announce themselves. They reveal themselves through consequences.
Disclaimer.